Today, we are going to trace the story of the formation of a system that we are all part of, the solar system. And for that, we will have to go back to before we existed, before the Earth was formed, and even before the Sun ignited. To form a solar system and ignite a star in it, the basic ingredient is always the same. You need mass, a lot of mass. The equivalent of 10 to 50 times the mass of our Sun, scattered over a volume several light years in diameter, in the form of a huge cloud of molecular gas and dust. Once you have that, all you need to do is wait for a trigger, like the explosion of a nearby star, to disturb it, or simply let time do its work by waiting about 100,000 years. The minimum amount of time estimated to be necessary for a fragment of this cloud to begin contracting under its own weight. Collapsing in on itself, the layers of gas will then accelerate the process, and the whole thing will start to spin, first slowly, then faster and faster. It takes about 1 to 10 million years for the combined effects of gravity and rotation to cause most of the matter to accumulate at the center in a condensing bubble of gas, while the rest gathers elsewhere, spreads out on a plane, forming a protoplanetary disk. Here, in this turbulent environment, all the matter that will give birth to future planets is already present, mainly in the form of tiny dust grains that will stick together and grow larger as they collide. In just a few thousand years, these tiny grains, under the influence of electrostatic forces or partial melting of their surfaces, will stick together and reach sizes of about a centimeter. They are the origins of future worlds. Give them a few more centuries, and some will become kilometer-sized blocks, which in turn continue to grow, collide, melt, and fuse with each other, aggregating into larger and larger blocks. They eventually form what are called planetesimals. These planetary embryos, about the size of the moon, begin to clear their orbits by slowly removing the dust found there. Barely 100,000 years have passed since the cloud began to collapse. More and more mass is concentrated at the center of the system, which now draws in a large portion of the surrounding gases. The matter that condenses and heats up there begins to collapse under its own weight, and gravitational contraction increases the pressure and temperature. The atoms collide more and more violently, and when, in this turbulent furnace, the temperature reaches 2 million degrees, hydrogen nuclei occasionally begin to fuse, creating an internal energy source that opposes the contraction. A thermonuclear reactor has ignited, and thus a young star is born. In its first moments of life, it is barely visible, deeply buried behind a veil of opaque gas that it illuminates from within. But soon, the heart of the system will stop attracting matter, because the light it emits and the solar winds that will follow will act like a snowplow on the surrounding gas and dust. The first millions of years of the young sun's existence are eventful. Highly unstable, it is in a phase called T-Tauri, and like most young stars, it begins its life with a pronounced adolescent crisis. In the space of a few days, or even a few hours, its brightness can suddenly change by as much as a factor of 40. Unpredictable and nervous, the young star is also prone to violent outbursts, which are manifested through the presence of a rapidly rotating magnetic field capable of propelling jets of matter through the system at speeds of up to 300 kilometers per second. The stellar winds and heat produced by the star are now pushing the gases to the outskirts, where gas planets are forming, although they are not really planets yet. But very quickly, their massive cores, which can reach up to 10 times the mass of Earth, allow them to attract hydrogen and helium from their surroundings, to the point where they become so massive that they are able to form their own accretion disks, a kind of mini solar system where their moons are formed. The capture of passing planetesimals could very well add other satellites to their realm. In the inner part of the system, only just under 10 protoplanets remain, which have almost finished gathering their material. The orbits of these bodies are still largely unstable, and occasionally some of them collide, either merging or breaking apart. This helps to reduce their number. And then, after a few tens of millions of years, the intensity of ultraviolet radiation emitted by the protostar has completely dissipated the remnants of the cloud that gave birth to the system. With no more gas left for the giants to consume, most of their growth is now over. Along orbital paths that are still not fully cleared, only blocks massive enough to have resisted the heat and intensity of the young star remain, whose mood swings eventually begin to calm down. And after about 10 million years, the star's layers of gas stabilize. The star has matured and has exited the so-called T-Tauri phase. At the center of the system that bears its name now sits the Sun, almost exactly as we know it. A stable star that has entered the main sequence, with its thermonuclear engine now humming on hydrogen. 99.8% of the material from the original cloud was used to make it, and more than 2/3 of the remaining mass ended up in Jupiter. As for the rest, everything else, it's about sharing the leftover crumbs. And with that tiny 0.05% of material left behind by the star and Jupiter, all the other bodies in the system were formed. Our planet Earth is still clearing its orbit. And it doesn't really look like that. It's molten because of the heat accumulated from repeated collisions, but also because of abundant radioactive materials in the early solar system, most of which sank to the center, where they still are, heating it from the inside. You could even say that it only partially exists because it's still missing 1/10 of its mass, which it will soon acquire in an end-of-the-world crash when it collides with another protoplanet the size of Mars. And after this collision, here it is, equipped with humans. Meanwhile, over hundreds of millions of years, the survivors of this cosmic billiard game seek equilibrium. The planets in the system, whose orbits are not yet fully stabilized, now engage from a distance in a dangerous game of influence. Under the sway of orbital resonances, in a chaotic and complex dance where the orbits are disturbed, the planets move, migrate, and disrupt each other. The four gas giants are then in a much more compact configuration and much closer to our Sun. And according to our models, Jupiter and Saturn push the orbits of the giants Uranus and Neptune into the Kuiper belt. The millions of icy bodies found there are disturbed by the arrival of the two giants. And many of them will then leave the belt and, in a swirling dance, rain down on the system's inner planets, which then find themselves under a heavy bombardment of comets and other asteroids. This constant rain of rocks from the sky will bring desolation to Earth, but also a considerable amount of treasure in the form of water trapped in the rocks, which will gradually fill the oceans. This event is called the Late Heavy Bombardment. The Moon still bears the scars of this today in the form of numerous craters. And finally, the orbits are stabilized and the system is practically complete. This gives us the opportunity to go see others, this time without using computer-generated images, because we actually have real images of protoplanetary disks in formation, which wonderfully confirm our theories about the formation of planetary systems. Here, in the Orion Nebula, several systems in formation have been discovered. Compared to the 33 light-year diameter of this structure, these systems appear as insignificant spots. Yet they already contain enough matter to ignite the stars within them and give birth in their wake to planets orbiting around. Below, we can make out at the center of this bubble the presence of a young star, whose light outlines the contours of the gas cocoon that surrounds it. Studying this nursery, which occupies a part of the sky 4 times larger than the full moon, allows us to retrace the history that was surely that of our solar system in its beginnings, the story of our cradle before it caught fire. Because for us too, everything must have started just like here, in a star nursery of this kind. From immense bubbles of condensing gas, like this one, which are currently drifting through space, and whose movement through the interstellar medium, rich in gas and dust, creates what look like shockwaves. By scanning the sky with our telescopes, we've even recently obtained perhaps even more striking images, those of planets feeding on their protoplanetary disks. These nascent systems are undeniably surrounded by worlds in formation, which reveal themselves to us through the grooves they leave in their wake. It's only been a few decades since we began to glimpse the extraordinary diversity of planetary formation sites. And given the number of them we've discovered, and the range of possibilities suggested by the variety in composition, rotation speeds, sizes, and masses of the clouds that fill the sky, it's reasonable to think we still have many surprises ahead in discovering other worlds. Who knows what this one might help to form? Perhaps hospitable worlds where one day someone might find themselves.
I'm telling you, our planet is flat, balanced on the backs of 4 elephants who themselves stand on the back of a sea turtle moving through the universe.
I don't know why, but I feel it's even crazier.
To stay tuned and not miss anything, remember to turn on notifications so you can follow the whole series. And if you like useful or pointless content, you can also follow us on Instagram, Twitter, or Facebook.